So good afternoon all. Welcome to session 4. So in the previous session we have discussed different things, right? So however in this session we will mostly discuss on, let's say, the cooking process, right? So that's what we are going to discuss here. So we will have a discussion on cooking process, and previously it's all about mostly what we did, fuels. We seen different types of fuels. We have seen different types of combination process. So we had an introduction, then we came to how we do the recycling, what are the different steps in recycling. Now then we came to the first process, which is the pre-processing, or we call it as a unit process. So in that we have seen different types of like combination, different types of enrichment process also, you can tell them, because whenever you are trying to increase the grade, for example you got different assay of metal in some ore. Now you want to increase, because you cannot directly put your ore into your whatever the parametallurgical or hydrometallurgy that we are trying to deal with, you cannot directly insert into it, right? So before that we need some process which can make less burden on the next process. So that's how we came to that, right? So different pre-processing process we have seen, right? So there are flotation, magnetic separation, settling process. So that's how we have seen those. Now moving on to the next process, which is, now we after that we even characterized. So what is, now how do you differentiate, right? Now once you got a product from a process, now how do you differentiate, how do you characterize your things? So whenever dealing with the powder particle size, we have seen different characterization techniques to measure the powder particle, right? We have seen the SEM, we have seen laser diffraction method, we have seen different types of process, right? Now, and the most basic one, which has been followed from like past centuries, so that is the sieving process, right? And we did extensive work on that. So how do you define any, um, like how do you define your powder particle size, right? So we did most of the work there, and we discussed a little bit about the SEM analysis, right? And so that's all about the characterization. Now coming on to the fuels, right? So you want to know, now you know what is the batch that is going in, now how that has came from. Now you know, now you want to know how to, like, so whatever the process you need to follow, you need some energy, right? Even it is for pyrometallurgy or hydrometallurgy or electrometallurgy, you need fuel, right? So if you are indeed use of energy, then there must be use of fuel. So now we will discuss the fuel, and we have discussed about fuel, what are different types of fuel. In this session what we are trying to deal is, we will see what are the different, we will talk mostly about coal, okay? So one type of fuel which is most abundantly used in steel making technology, and right, in steel making or iron making, you can take, which is coke. Now coal and coke are two different things, right? So coal and coke are different. Now coke has higher carbon, which gives more thermal energy when compared to the coal, right? Now why? Because we are trying to increase the carbonaceous content, right? So coke has more carbonaceous content, right? Now how do we arrive to coke, right? So what we do is we take caking coal, right? So we make cakes, right? Nothing but you form a compact of, with pitch blende or tar or anything, or water, moisture also, we can take water also, to make a green compact, and then you heat it in the absence of air, right? So that is what coking process is. So let's say the temperature is between 1000 to 1200, right? So what does this do? Whenever we do this treatment for 2 to 4 hours, so first it will remove your moisture, right? It will remove your volatile content, right? And also it will make you porous because the things are getting escaped, right? So this is called as carbonation process. And the other name for this is the destructive distillation, which I have also said before. Destructive distillation. Right. Now there are this is about destructive distillation. Now why we do this because you need to form a hard substance, because uh, yeah, so you need to get a very hard substance and also porous substance, and by doing this you are trying to remove the moisture and volatile content, because whenever you directly put coal doesn't have that much impact strength, and also coal doesn't have uh, the coal has less carbonaceous content and the more moisture and other thing. So what we are trying to do is we are trying to remove, right? Right, so we are trying to remove everything from it so that we get a concentrated carbonaceous content, right? Now right, so moving on to that. Now how did this happen? So what we do is we take so we have a cylindrical retorts, you can call them, or cylindrical chambers, rectangular chambers, right? Now you heat it, because you cannot heat directly, it is indirect heating, right? So it is an indirect heating, so heat travels from here, from this one end to the center, right? So here what the some of the volatile things will come out, so then you will have a hard mass. Now the next thing we need to understand is where this is actually being used. It is used in uh, mostly blast furnace, right? Because you deliver both your iron ore and coke. So first you form pellets in like iron making. You first form pellets, right? So that is important. Then you those the pellets also are like a of a definite shape, and they are also mixed with your both coke and iron ore. It's not like a single pellet of that. So it contains both. Now, so just like you will have different batches side by side. So in between you have your heating zone. So you heat by gases or right, and this is very narrow. It's not like very huge, because again you will have a large thermal gradient. So again, which is not necessary. We do not want that. So it is 12 to 14 hours, not 2 to 4 hours. Okay, right. So now for there are mechanical ways. After getting coke, there are some plates which take you out. So there are oven doors. Now, how do this happen, right? So at first you will have your this chamber, and then you have heating chamber here, right? And then you have regenerators below, right? And then you charge it from either from sideways or from top, and then you quench it, right? So there are also byproducts. So you collect, you can have coke charge here, also you have coke charge, and then you have byproducts. right? And then you have pusher car, which takes out the coal once the batch or process is being done. So what are the things that we contain in your coal? Coal, right? So caking coal, we can call it. What are the things that you contain? So first, when you heat it from 0 to 300 degrees centigrade, you will first remove the moisture. Even after 120, the moisture gets coming out, and also your volatile matter. In last class, we also learned that when we heat between 400 to 500 degrees centigrade, your coal becomes a plastic mass, right? And above like 600 degrees centigrade, it will start converting from plastic to hard, or you can call it as semi coke. It contains some hard mass, has hard points at somewhere, some plastic points at somewhere, and after your 1200, like if you reach of 1200 degrees centigrade, so everything becomes coke, from semi coke to coke, right? Now there are different ways you can charge. I have said before, right? From you can just throw it from top, or you can distribute top wise by using rotating floor. So it will form a spiral type, you know. Or you want to have circular sections, you can have circular sections, or you can directly charge it, you know. So there are different types of charging, right? Now in stamp charging, what we do is we prepare everything beforehand, right? So we will not leave anything, so we prepare everything beforehand. What we do is you make fine, and then you so first we will make fine coke powder, coal powder. Then we make a perfect bed, then we push it. So that's what we do. We make a fine coal powder, then we make a bed of a packed bed, and then we'll push it. So that's what we have in stamp charging. Now there are different ways to test the coke strength. So one is the shatter test. So what does shatter test tells? The name itself suggests. It will tell you your impact strength, right? Impact strength, right? And if you want to know the wear, right, you need to do tumbler test. So in tumbler test, they undergoes they undergoes the surface to surface shear. So here's what happens in tumbler: there will be a big drum, and it will start rotating. So in shatter test also the same thing, but you will have lifters. You know, so what does when you have a drum? What does the lifters do? These, whenever it comes down, it will take spotter particles with coke particles with it, and after reaching top, they starts falling down. Some might land on coal particles, some might land on different one, so they will break. Now what you do? Now you take, or you can just do the drop test, right? Right. In drop test is nothing but you take it to certain height, you throw it from top, right? And they start hitting. When they start hitting the surface, they will break. And in the tumbler test, you have a drum, it start rotating, and when they fall on each other, again they will break. So that is one thing. And also the powder particles are in constant rolling, right? They start rolling from on the surface, and because of that, you will also have wear, just like the tires of a car. When they roll on surface, right? So they roll on road, and after some time you will start wearing off your rubber tire. So the same goes here also. Now what you do is, again we come back to our sieve analysis. We take it depends upon size what you want to take. So let's say we take 75 to 50 mm. That means the size is less than 75 and greater than 50. So it is between, so the average size should be what 5, so 125, right? So it is 67.5, the average particle size, right? Even though it is not right. So what we do after that, we do the SEM analysis, then we find out the size of each particle, or you can use software, right? Then you find the average particle size. That will give you a bit more size closer to the actual value, right? Now there are different types of ways you can define it. There is also the shatter index, right? In shatter index, you measure what is the weight of coke surviving after your whatever the coke that has remained after your 50 mm, right? So this mesh has some number. So whatever the retained powder particles above 50 mm you will take, and then you divide it by total mass, right, in times 100. That will give you that. Now if you want to know the wear resistant, then the wear strength, then you do the tumbler test, right? In tumbler test, what you do is you take a 40 mm screen. So whatever the powder particles that are remained in the powder particles that are remained in your 40 mm screen, then you get them, okay? Before 40 mm screen you will get it, right? So that is about so then you called as a MICOM 40 or M40 index. And then there is also this 10 number. Sorry, next. You will have weight retained above 40 by total by initial weight, right? The same weight retained about 10, you will get initial weight times 100. Then that M40 represents your tumbler index, while M10 will tell you the abrasion index. So that's how you do, right? Right. So right, we need to consider all those things. Now whenever you do mass balance, we need to know what are the different types of what is the input, so what does it contains, and what is our output, right? So whenever you so this is your heating chamber. So you first involve your coal, right? This is your coal, and then your out will be, so you will have your flue gases, that means your byproduct, right? So you have your fuel gases, I mean the gases which are been like combust, right? So once you get it, after the coking process you will quench it. So for that quenching you can have a water or inert gas, right? So whenever you try to screen it, whenever you have evaporating motion, you will have some breeze or some fine powders which suspended in air. We call it as a coke breeze, and finally you have coke, right? So we didn't involve any byproducts for now, right? Now we are only considering about the coke part, okay? So let's worry about the other thing. Now at first you will have quenching. Once you get the after doing the coking process, you do the quenching. That means you remove, so you add water or inert gases, then you cool it down, then you do the screening for your next process, whether it is iron making or coke making, okay? In iron making it is your primary one, in coke making it will be your secondary fuel, right? So and then you have coke. Once you do the screening, then you will have coke grease, right? Then finally you will have coke. Now what about the gases that you are getting? Now you have very high temperature because of cooking is happening at 100 degrees centigrade. Now what you try to do is you try to condense. A condenser is nothing but a very long tube, or you can have a long tube, or you can have a helical tube. Just you are increasing the surface area and you are taking the heat out, right? So once you condense, some may be volatile, some may be not. So which are not volatile, we will convert into either liquids. So that is called tar, right? And again you cool it further, right? So then you do the distillation. Distillation is again, once you get a total liquid, you depending upon the temperature of depending upon the boiling temperatures of the different tar is nothing but not a single liquid, it contains different types of liquids, right? So depending upon the boiling points, you selectively take out, right? For example, first you cool it, then heat it. So when you are heating, or you can just directly cool it in a such a way that once you reach like 100,000 degrees centigrade, A will get liquid, right? Because the boiling point is high for it. And once you reach 800 degrees centigrade, B will get liquidify, right? So liquids come out, the gases will go down or up, right? So after distillation, you will finally have a pitch, and then you will have volatile fractions, right? You might have benzene or toluene or naphthalene. Okay, then you have gases. Again, you have scrubbers. Scrubber, you add water, right? So and then you have scrubbers such that you can separate the aqueous ammonia. You will get ammonia, right? And these gases are further go into purification. Right. Different types of distillation. You have one H2S, hydrogen sulfide, which is further oxidized to get sulfur, and then you have hydrocarbons, right? Hydrocarbons and hydrogen. Now these gases can be used to heat the chamber, right? By burning it, you can get that. So these are the different byproducts that you get. It depends upon the process that you are following to get a certain compound, right? If you have volatile things, then you can directly separate them, right? So these gases cannot be separated, right? These gases you cannot do the volatile for this guy because they're methane, so their boiling point is very low, right? So you can, once you cool it a little bit, you can get the liquid substances which are the coal tar, and then depending upon the and again following the distillation, you will have benzene and toluene, very high molecular weight carbon molecules, right? And whatever the gases that have been remained after certain cooling, then you separate ammonia out by using scrubber and adding water. So after that, finally you will have total, all gases, right? So in those gases you can have hydrogen sulfide and hydrocarbons that can be again separated. Now we know the different outputs. Now let's do the mass balance and also find calorific value. There are different types, right? We have studied calorific values, the gross and net, right? So net calorific value will take out the gross value will tell you the amount of energy that is produced when you burn, when you completely burn or oxidize compounds, right? So hydrogen is being converted to water, and carbon is converted to carbon dioxide, and also we are not involving the latent heat part, right? So whenever you try to burn it, so there is also this water. So water will also take up energy. Water vapor will take energy and it will become superheated steam. So again, some amount of energy is lost there because steam takes energy, right? So in net calorific value, we avoid that part. Okay. Now, so at first, let's do the mass balance. Let's say you have coke oven, which is at certain temperature. Now let's say I have involved my coal. So this is an example problem. You might get problems like this in your assignment also. So let's do it now. Let's say I have a carbon of 76, hydrogen of 5, nitrogen of 2, sulfur of 2, so 2.8. So it already have the moisture of 6% and ash is 6.2%. This is my initial coke. Okay, and then from that we get a coke. Okay, so C is 85, H 2, nitrogen 1, oxygen 2, sulfur 1.5, ash 8.5. You can see there is no moisture because at 100 degrees centigrade you will not find any moisture there. After that you will get a tar, which has again coal of 5%, right? So coke, in that coke will be 89, hydrogen will be 5, nitrogen will be 1%, and then you will have gases. These are based on volume percent. You will not talk weight here. So you can have benzene, methane, ethane, right? Ethane. And then you some uncombusted carbon, some combusted carbon, fully combusted carbon, then hydrogen, nitrogen, oxygen, ammonia, and finally H2S. Okay. So these are the different products that you get. This is your input. This is your output 1, output 2, output 3. Now let's say the amount of coal, let's say you want to make a coke of 1000 grams or 1 ton. Right? Then how much coal is required to get 1 ton of coke? So how do we deal with that? See, you can take different compounds. So for example, if I know what is the amount of carbon initially was there, and if I know what is the carbon at final remaining, then if I talk about carbon, then I need to consider all the carbon compounds that are here, right? So if this is my input, then how much is my output, right? Or you can also take single one, what is the amount of carbon from which you can get this much, right? That will also will tell you the coke, the amount of coke that you are getting. So, right, or the best one is to take the one compound which is not involved in different outputs, right? So let's say if I take ash, see it is only involved at input and it is involved in output, right? You can do that mass balance and you can find the amount of coke that is necessary. Or if you want to involve the carbon, then you need to involve all the carbon containing compounds to do the mass balance, right? Again, that is not a suitable process. Okay, so instead of that, we need to involve a certain compound which shouldn't make our like problem much complicated, right? So nitrogen, you can see it is involved in four stages, right, in all the outputs and input. So what about sulfur? Sulfur is again also involved in two outputs. So sulfur, you can take sulfur, right, because in here you will not find sulfur. No, again there is a 5% of coal, right? So again you cannot involve sulfur here. It is also again involved in 3-1. Moisture, right? So here again you will have hydrogen, so yeah, that is again a problem. So the only option is you consider ash, right? It is simple mass balance, input equals to output. There is only one output, right? So what is my input? So let's say the amount, the x, let's say x is my weight required. Okay, so x into how much is that? 6.2%, right? So it is 0.062 equals to how much is our coke that we finally need? We need 1 ton times 0. It is 85, 0, how much is that? It is 8.5, so it will 0.085. If you multiply with 100, it will be 8.5. So I used direct values. Okay, so if you calculate, x will be, so 85 by 62 into 10 cube, so that will be approximately 197 kgs, right? So this is the amount of coal that you need to get 1 ton of coke, right? Now the next question will be, what is the percentage of S distributed in coke from coal, right? So what is the amount of S that is coming from coal into coke, that we need to find, right? So now we have defined our coke that I am getting is 1000, right? 1 ton. Okay, so what is my S, weight of S in coal? How much is it? So coal is my 1370.97 into 0 point, how much is it? Sulfur 1.5%, right? No, we are talking about coal. Coal is 2%, so 0.02, right? So this will give me, let me calculate, 1370.97, yeah, it will be 27.42. Let's write it in kgs. Now same goes weight of S in coke, right? So it is 1 ton times 0.015, which will give me 15 kgs. Now what is the distribution? You just divide 15 by 27.42, and that will be 15 divided by 1.42, 54.7%. So this is my distribution of sulfur that is coming from coal into coke, right? Now my third question is percentage of heating value of the coal obtained on burning coke. Let's say we are assuming complete combustion. The incomplete combustion will come after. We'll discuss that. We'll discuss those type of problems. Okay. Now, what is the percentage of heating value of the coal, right? So now last time we have discussed Dulong formula, but we don't know how do we got it, right? So there was no derivation explained. So we will do that here. Right. So let's do it, right? So let's first talk about GCV, or gross calorific value, right? Now how do we get that? Now we need to involve the compounds that are getting combust, right? What are the compounds that are being burned or undergoes combustion, right? Carbon, hydrogen, and you have your sulfur. So these are the three main compounds, right? So that's what we have been discussed. Nitrogen is inert, so it will not undergo any reactions. Hydrogen is getting burned, carbon is getting burned, sulfur is getting burned, right? So either way you are supplying oxygen, so we will not involve oxygen here, we will even remove that oxygen. Okay, so let's say this oxygen will already react with hydrogen. Okay, so we will discuss that. So these are the three important ones. There is also oxygen, because we are supplying air, right? So we will remove whatever the amount of oxygen was there initially by reacting with hydrogen giving water, right? So we need to remove that part of hydrogen that is getting react with your oxygen, right? First let's do this one. So whenever carbon reacts, so for now we are talking about complete combustion, let's not involve any exam. So it will, on complete combustion, it will give you carbon dioxide. Now hydrogen on complete combustion will give you H2O. Sulfur on complete combustion give you H2O. On further combustion of sulfur you will also get SO3. So we are not going to involve that part now. So these are the, let's stick with these three reactions, because these three reactions that we have seen. Nitrogen is inert, it will not react. Ash is also react, it will not react. Moisture, it will take up heat but it will not react. So these, we are assuming all these three compounds are being inert. So the only elements that are undergoing any combustion here are these carbon, hydrogen, sulfur, right? Now how do we get the calorific value, the gross calorific value? So whenever 1 mole of carbon reacts with 1 mole of oxygen, will give you 1 mole of carbon dioxide, and that will give you the enthalpy of a reaction, which is equals to 8080 kilocalories per kg. These are standard values, you can look it up in net or the combustion chat. Okay, so this is on kilocalorie. If you want to have in joules, so 1 calorie equals to 4.186 joules, right? It will multiply it by that, then let's assume it is 4.2, then 880 into 4.2, that will give me 33,700 kilojoules per kg. Like, let's normalize them. Let's normalize everything to per kilogram. Okay, that will be helpful. Again, H2 will react with half mole of O2 and gives you 1 mole of water. And for this the enthalpy is 34,000. The amount of heat that is generated whenever you burn hydrogen plus oxygen, it will give you this much amount of energy. And the same goes for the sulfur, which is 22040 kilocalorie per kg. Now this is the amount of value that is, so our calorific value, or GCV, gross calorific value, will be. And if I'm talking about the percentage of like, for example, if I have a Coke, so everything is mentioned in fractions, right? So if we mention in that way, then this will be divided by 100 times the amount of into the percentage of carbon, that is one part, plus now we need to understand, let's add one more slide, the hydrogen part, right? We know 2 grams of hydrogen is required to react with how much? So oxygen weight is number is 8, so times 2, 16, but oxygen molecule is 32, and because only half mole is being used, so it is 16 grams of oxygen to you 18 grams of water, right? Now what about if I have X grams of oxygen, right? Then my hydrogen that is required will be x into 2 divided by 16. So 2 1 2 8. So this is my amount of oxygen or amount of hydrogen that is required to react with x grams of oxygen, right? So let's say my oxygen content is Y, okay, or I can say O. Then the amount of hydrogen that has been depleted or reacted will be, this is the percentage of H that initially was there, minus the percentage of O by 8. This is the amount of hydrogen that has been reacted with oxygen to form H2O, right? So we are removing that much of hydrogen from our total value of hydrogen that is present in our Coke, plus 2240. So everything are written in kilocalorie, okay? We are not involving kilojoules, okay? So kilojoules will give a larger value, okay? So that's why, because it is 4.2 times of your calorie value. So that's why it's better to mention energies in terms of kilocalories rather than joules, okay? So 2240 times the percent of S. So when you divide it by 100, so that's why in the slides we have seen 81, and when divided by 100 you can approximately equal to 34, and you can write it as 22, okay? So that's why we the large numbers weren't written there. So this is our gross calorific value. Now if you want to know what is our net calorific value, right? So a net calorific value will remove the latent heat of water vapor that is formed during combustion, right? So that's why our net calorific value, or a lower, you can call it as a net calorific value or lower calorific value. Why? Because it is less, because we are subtracting some amount from this, right? So there is gross calorific value and there is net calorific value. Net calorific value is something less, right? That is, let's say that is Y. Let's calculate what is that Y, okay? So what is this subtracting variable? That is the latent heat of water vapor formed during combustion. So this is latent heat of water vapor formed during combustion. Right. So let's say again, let's write the equation: half O2 plus H2 H2. So 2 grams will give you 18 grams of water, right? So 1 gram, that means 1 H, will give you 9 grams of H2, right? Or half mole I can write, right? So whenever you form the water, so that is, so the enthalpy is 587 calorie per gram, okay? So this is the amount of latent heat that you get by forming water, okay? That's right. So 1 part of hydrogen burns with 8 parts of oxygen to produce 9 parts of hydrogen. So therefore 1 part of hydrogen produces, let's say if I am talking about in percent value, right? Because everything in Coke was given in percent, right? So that is percentage. That means H by 100. That means this will give me 9 into H by 100. Right? So this is the part of heat that has been escaped by water vapor, right? So this will give me 0.09 H into 587 calorie per gram. Okay, if you wanted to convert into kilograms, so you just multiply it with 1000, right? So it will become kilocalories. If I am at 587 kilocalorie per kg, okay, so what about kg? Now my NCV, net calorific value or lower calorific value, what does it represent? Again, it represents the heat available when water vapor escapes, right? So that is the amount of heat that is available for us. Right, so that will be GCV minus mass of H2O that has been formed times the latent heat. Right, so this will give me GCV minus H. Let me calculate. So that will be 0.09 times 587, that is 52.83 H into 52.3, right? So this will be kilocalorie per gram kg, because everything we have mentioned in kilograms, right? Yeah, everything we have mentioned in kilograms, so it's better to mention everything in kilograms to avoid any ambiguity. Okay. This is kg. Okay. Now this is the difference between NCV and GCV. Now this is about the NCV and GCV derivation. Now moving on to the formula that we have been doing. Okay, so how much is that? Yeah, now you know what is our NCV value. NCV will be how much carbon is there. So value, yeah, so actual value will be 1 by 100. Let's divide it by 100 now itself. 80.80 into what is the percentage of carbon in coal, that is 76. Okay, and because I have divided by 100, so now we can directly write 76 instead of writing 0.76. Okay, now plus 345, right? 345. So we dividing by 100, so it will directly, two zeros will go away, times what is the amount of H that actually is present in coal is, how much is it? H that is present 5, right? And oxygen is 2.8. 5 minus 2.8 divided by 8 plus 22, it is a calorific value, 2240, right? 22.4 into what is the percentage of S, that is 2%, right? Now minus the amount of H2O that has been produced, right? So 5.87 times 9.9 into 5, because that is 5% of hydrogen is there, right? Plus we also have moisture, right? So that's why we are writing 6. what will be our final NCV? That will be, let me calculate, so 80.8 into 76 plus 345 into 5 minus 2.8 by 5 plus 22.4 into 2 minus 5.87 into whole bracket 9,545 plus 651, yeah, 51. So that will give me 7,513.6 kilo calorie per kg, right? This is the value you get. This is approximate value, right? So now what is my heating value? Right, so heating value coming from 1 ton of heating value of coke, right? So it will be, just multiply this with 1000 and that will give you coke value, right? Oh, this is for coal, right? Yeah, this is for coal. If I burn this coal, then this will be 1,3, because if I take out the kg term, then I have to multiply with this guy. This is the amount of coal, right? This much into 7487.81. You'll have this value, okay? And that is 10. You have to use this value, and finally we'll have the total heat. Okay. Now, in slides, the relation is slightly changed, right? Instead of 80.8, we have written 81, right? Let's follow that. You can have direct values, or you can just normalize them, okay? So that the numbers are smaller. 81 times 85 is the amount of coke that is present, right? 85, 2 and 2 to 1.5, okay. So 2 and 2 and 1.5, right? So heating value of coke will be 341, percentage of hydrogen, again percentage of oxygen, then percentage of sulfur will be 1.5. Instead of writing 34 point something, we just write 341, and again 22 point something, we just write 22. These are approximate values, okay? So times 1.5, right? Is there in coke, do you find any again we are talking net, right? So there is no moisture, that's why you can directly write 9 cross 2. Okay, so this will give me so why we removed? Because whatever the left oxygen is getting away here, right? Some steam is forming, right? So those hydrogen oxygen get react and form water there itself. So that water vapor we are trying to remove it by minus sign. Okay. So actually the oxygen should react with whatever the hydrogen was there. So this is the amount of oxygen that has been, this is the amount we removed, right? So that oxygen is reacting with that hydrogen to form this much amount of water. So this thing we have removed. So that's why net value is somewhat lower. So this will be, NCV will be, so this 31.85, this will be 4, and 2 minus 0.25, which is 1.75, plus 22 into 1.5 minus 5.4 into 18, right? So this will give me 0.63 kilocalorie per kg. Now for 1 ton coke, simply 0.63 to 10 kilocalories is the amount that you will put. So initially this was the amount that has been produced, but from that something is lost, right? So let's calculate this guy. 7510.67, so 1370.97 into 7510.67, right? This is, let's say this is y at 740963 divided by this y value will give me 70.31%. Okay, so before we have taken a different equation was slightly different because we were taking approximate value, exact values, so that's why we got a different value from the slide one. Okay, for this value it is same because we followed the same relation, right? Now the final question will be, what is the final question? Amount of coke oven gas produced, right? So amount of gases that has been produced, right? This is our final part, fourth question, right? Amount of gases that has been produced. Now how do we do it, right? You take one compound which is again not present, because if we take a carbon, that we have to do all the mass balance, we need to know all the fractions, right? What about hydrogen? Again we need to know what is the amount of hydrogen here, hydrogen here, hydrogen here. So the best to do the mass balance is here, take the sulfur, right? If you take the sulfur, you can directly relate, right? So you can directly relate, we have sulfur here and sulfur here. So we know amount of sulfur is present in coal, 27.42. So that will 27.42, and also we have sulfur in coke, and that is 15, right? That will give me the amount of sulfur that is left. So this is 12.42 kilograms of sulfur is present. Now in question they have given that H2S is only 1.84% of CO, I mean the coke oven gas. Question, let's say this is given. If we don't know that, then we cannot do it, right? So we need to know at least one composition of the gas, right? So 1.84 of coke oven gas, right? So let's say the coke oven gas, the amount that has been, let's do everything in meter cube, right? Let's not involve liters, let's do everything in meter cube. So I will write values. 1 liter will be equals to 1000 centimeter cube, and 1 meter cube will be equals to 1000 liters. Okay, at standard temperature. Let's these are the conversions for centimeter cube to meter cube and meter cube to centimeter cube. Okay, now so amount of coke oven gas will be Y. Then H2S, the amount of H2S that has been formed will be Y into 0.0184. Right? So this is the amount of sulfur that is left. Right? Now what is the amount of sulfur that is present in H2S, right? And sulfur weight is 32, hydrogen is, so hydrogen atom is 1 plus 1 2, so this will be 34. 34 grams of H2S contains 32 grams of sulfur. What about if 12.42 grams of sulfur contains, right? So this is my X. So 34 into 12.42 divided by 32 will give me the amount of H2S. Amount of H2S in what? In kgs. Now if I convert into moles, that will give me 34 into 12.42, right? So it will give you fraction, right? It will give you H2S. 34 grams of H2S will give you 32 grams of S, and 12.42 will give you 0.388 kg per mole. Let me calculate. Okay. So I have 34 into 12.42 divided by 12. It will give me 35.19 kgs of H2S. Now we need to convert into moles, right? So to convert into moles, again I need to divide it by 34, right? So 35.19 divided by 34 will give me, okay, maybe we did a mistake, 12.42 divided by 32. It is 0.388 into 125. So yeah, 34 will, again if you divide it by 34, we will finally have 0.388125 moles of H2S. Now we know 1 mole takes 22.4 liters, or 22.4 into 10 to the power of minus 3 meter cube, right? So you multiply it with this value, so that will be amount of cocoa gas will be, how much was there? So this is my Y, right? So Y will be 22.4 into 0.388125, right? Minus 3. Okay, so okay, if it is volume percent, if 1.84 is a volume percent, right? So then you just multiply 0.388125 divided by 1.84 will give you 21. Sorry, I forgot 22.4 and 24, right? So this will give me 2109.375 into 472.5. Yeah. So finally 72.5. Yeah. So this is our final value. Now this is about mass balance. Okay. Now moving on to the combustion, right? Let's move to combustion of fuels. Okay. Moving on to let's say the combustion of. Now we will see the complete combustion, incomplete combustion, different types. Okay. So whatever we have discussed before, right, in session 1 and session 2 are unit operations, right? So there is no, like, we are not changing any chemical structure, we are only changing the physical form. Okay, and we just play with their physical properties. So that's what we have seen there. Now coming to combustion of fuels. So to combust or to burn anything, you need what? Oxygen. Now where do you get oxygen? You get it from air. So before moving into it, let's define what is the percentage of oxygen. Let's standardize that. Okay, it depends upon quality of air where you find, right? So let's say my nitrogen percent is 79 and oxygen percent is 21%. Let's say this is my 8%. Okay, totally it will become 100. Now there are different ways. So if you want to burn your fuel, you need to mix your fuel with air, and depending upon the mixture of the mixing, you will have different terms that you define, right? Depending upon your mixture, you will have your potential energy of fuel, you have thermal efficiency. If you mix more, if you mix less amount of air, then it will be an incomplete combustion, because let's say x moles of reactant species are, let's say RS reactant species, okay, are present in my fuel. It needs Y moles of oxygen to you make products for this is my stoichiometry. So X requires Y moles for a complete combustion. That is, this is my stoichiometric ratio. And if I have less Y, then my fuel is high, right? So X divided by Y is my stoichiometric ratio. Okay. So if my Y is less, then X by Y will be greater than 1. Right? Then you will have incomplete combustion. If Y is more and X is less, then you will have complete combustion, and again you will have some part of air, right? And whatever the thermal energy is there, that is again going to heat whatever the air that is present. You need to supply more heat, right, to heat the air initial products, right? So yeah, we'll come to these terms later. Okay. So what are the products that we have seen? Let's define these products. So we have seen elements: hydrogen, carbon, sulfur, right? Sometimes in some fuels nitrogen also can react, right? So hydrogen will give you water, carbon will give you carbon dioxide. If it is incomplete combustion, you will have carbon monoxide, you will have sulfur dioxide. If you have a very excess amount of air, then it can form sulfur trioxide that can be reacted with H2O, which is a famous reaction, and form sulfuric acid. And nitrogen is there at high temperatures. It can form nitrogen oxides. It can be NO2, NO4, depending upon the amount of oxygen, partial pressure of oxygen, right? And also if air is less, then you will have, if air is too low, then you might have carbon that is unreacted, right? And there is ash, which is non-reactive. So these are the reacting species. Okay, we haven't considered this nitrous oxide, so let's avoid that. So complete combustion, So complete combustion is nothing but you completely convert whatever the reacting species, whether it is carbon, it is hydrocarbons, to carbon dioxide and water with full release of its thermal energy, right? Which is GCV, gross calorific value. Now, incomplete combustion happens when you do not have amount stoichiometric oxygen less than your stoichiometric amount of oxygen is there. Then you can form carbon monoxide. Again, this carbon monoxide, if there is excess amount of there, it will form carbon dioxide. And this carbon monoxide can react to give carbon dioxide. Okay. This. Mm, or at some temperatures, the carbon dioxide will react with carbon to form CO. Or that's why at lower temperatures, the carbon dioxide is unstable. Okay, so it redeposits the carbon. So this is the famous reaction called gasification. You can call it as a gasification reaction also, because at one stage you have carbon, you have solid, and some carbon dioxide that is reacting to give carbon monoxide. Right, everything is converted into gasification reaction. Okay, so right, this is about the gases. Right, for solid fuels you need to have a fine surface area, because you are reacting with oxygen, right? So you need more and more surface to air ratio, I mean surface to air area, right? So that's why you need fine solid fuels. But in liquid fuel, sorry, not liquid solid. So liquid fuels, what you can do to increase surface area, you can disperse them by doing atomization. Atomization is nothing but you have a liquid, and let's say this is my liquid, which is stored in a container which has a small hole. Initially it is very small orifice. Initially it is closed, and then you apply air upside, okay, from bottom, okay, from top surface. Then what happens, the pressure is increased, and because the area is very small, the velocity, again you can use a1 v1 equals to a2 v2. So a1 is very much less than a2, then v1 should be very much greater than v2. So that's what happens, right? So when you have very small surface area, then the liquid will squirt out or burst out. So that's what we tried. We can split water in two ways, right? One, you can have a very turbulent flow, or you can just store water and then push your water with air by gently opening your mouth. So then the water particles will get dispersed, right? It will not follow a single path or a single flow of water, right? You will not find that. You will have a dispersed kind of thing, right? So that's what happens in atomization. And very interesting part about atomization is this is a process by which you form glasses of metals, right? We know from metallurgy, whenever you cool metal pool very fast, like 10 to the power of 4 Kelvin per second, 10 to the power of 5 Kelvin per second, or 3 Kelvin per second, 10 to the power of 3 to 10 to the power of 4 Kelvin per second, then what happens is you will form metallic glass, right? And to cool it very fastly, you need to have as large amount of surface area as possible that can be attained by very small droplets, and that is done again by atomization. So a copper melt pool was first initially taken during the first initial experiments. It was pushed through an orifice. You form an atomic crystals of atomization, and you have a crystals of, not crystals, glasses. So they formed a copper glasses. If you follow this process, you can do it. Okay. So that is about atomization. Okay, coming back to our the terms. So one is the equivalence ratio, right? Equivalence ratio, which is 5, and 5 will tell you your, let's write F as a fuel and A as air. So fuel to air mixture, air ratio, divided by again fuel to air ratio. This belongs to stoichiometric conditions. This is the actual, I mean that we have mixed, right? So if this value, so this is fixed, right? This will not change. Now what I'm trying to do is I'm trying to increase air in my composition, then this value will decrease. So again, if this decrease, then this by divided by this will again decrease. So 5 will be less than 1, and we call them as fuel lean mixture, because it's obvious, right? Fuel is less when compared to stoichiometric ratio. And if I'm trying to increase fuel, right, then this value will increase. So then 5 will be greater than 1, then that is called as a fuel rich mixture, right? So this is one term that we define. Okay, so again, let's take an example. CH4 will react with oxygen, which gives to carbon dioxide, yes, H2. Now you need 2 moles, so it is balanced. No, it is balanced, right? So 2 times 4, 2, 4, yeah. Now we are not supplying only oxygen, right? We are supplying air, right? So that's why you also need to involve the nitrogen. Now what is the equivalence of nitrogen that should be present? Now we know you need 21 grams of oxygen is used in, for example, there is 100 grams, and 21 grams of oxygen is equal to 79 grams of nitrogen. This is our air composition. Now if there is 2 moles of oxygen, then 2 into 79 by 21 moles of nitrogen must be present. So that's why you keep a bracket here. Then 79 by 21 will give me the equivalence of nitrogen that should be present, times 2 will give me the amount of oxygen that should be present with nitrogen in an air of a composition of 21:79. So yeah, so this value, please remember this value will be used in many problems. So 79 divided by 21, let me calculate. 79 divided by 21 equals to 3.76. Okay, this is the equivalence ratio. So 2 into 3.76 grams of, moles of nitrogen is required, right? Now, so what is my equivalent weight of methane? Equivalent weight is nothing but the weight of a compound of 1 mole. 1 mole weight 1 mole compound, right? So equivalent is nothing but weight is equals to your molecular weight. Okay, so if it is 16, then this will be 16 kgs of fuel. Okay, so what is the amount of oxygen? Oxygen weight is 16 times 16 times 16, 32 times 2, 64, right? 64 plus 79.21, right? 3.76 times 14 to 28. So 28 nitrogen weight is 28. Okay, and that will give me 28 times 3.76 will give me 210.6 kgs of nitrogen. So 16 kgs will require 274.6 kgs of air, right? Or 1 mole, or you can call as 1 mole of CH4 requires so So 210 plus 64 will be 274.6 kilograms, right? So if I divide it by 2, then it will be 1 2 137.3, right? So 2 7 14, 2 3 6 7, yeah. So 1 mole of CH4 will require 2 moles of air, right? So because 137.3 is 1 mole of air. Wait, is it 1 mole of air? Yeah, it is 1 mole of air, right? Because oxygen is 16 times 32, that will be 32, and nitrogen is how much? Oh no, it is not 1 mole. Okay, so let's remove this guy. So 32 plus nitrogen is my 28, right? So if I multiply with 0.21 into 0.79, this will give me 1 mole. Okay. Yeah, so this will give me 1 mole of air that is present. Or you can just multiply for 100 moles, you can just multiply with 21. Okay, so that is not an issue. Now you know what is amount of fuel that we are mixing with air. This is the amount of fuel and this is the amount of air that we are mixing. And if you want in terms of mole basis, you can convert that, so that is not a problem. Okay, or you can even do in volume ratio also. And there is also this another term called as the relative air fuel ratio. So that is just a reverse of what we call equivalent ratio. Okay, so that is the reverse of equivalent ratio, and the percent theoretical air, okay, the percent theoretical air will be equals to 100 divided by 5. This is the percent of theoretical air that is required. Now if you want to know what is the excess air, let's say I have supplied more amount of air than my excess air. Okay, so if you know the ratios, okay, air to fuel ratios, let's say my air to fuel ratio for actual is my, let's write it as AFR actual minus AFR stoichiometric divided by AFR stoichiometric into 100 if I am talking about percent. Now what does that mean? Air by fuel actual minus air by fuel stoichiometric divided by air by fuel stoichiometric. Now let's say I am adding more amount of air, right? So if I am adding more amount of air, then what happens? Let's write air by fuel ratio as A by F, air by fuel, okay, air fuel ratio or A by F, or you can take it as this one, this guy also, equivalence ratio also you can take it. So let's take it in equivalence ratio. Okay, so that will be my F by A, right? Fuel by air ratio. You can even take that. Okay, one you can take this or you can take that. That one also. Let's take A by F. Let's write it as like this. So fuel is constant. We are not changing the fuel concentration. I am only adding extra air, right? So F is constant everywhere. So you can take F out on both sides. So fuel gets cancelled. So A actual minus A stoichiometric divided by A stoichiometric. So what does it give? So it will give me A actual divided by A stoichiometric minus 1 into 100. So that will give me the XSI. Right? That is what we do, right? The percentage of XSI, not just XSI. Okay. Now if you want to XSI, you just remove this 100. You will have XSI. Now there are limits of flammability. That means you cannot have very lean amount of air in your fuel. Even though some amount of air is there, the fuel will again combust. Even though it will not undergo complete combustion, it will start reacting. But there is certain limit up to which you can decrease your air value. Apart from beyond this, you cannot below this you cannot decrease. Okay, the reaction itself will not start. So that is called as the limits of flammability. Okay, so that is about that. So what are the stages in the combustion? You first stages of combustion. First you mix the fuel plus air. There are different ways of mixing. You can create a cyclone, or you can create a rotating gun. There are different ways you can mix, right? Then what we do, you ignite by giving some source, either it is a spark. For example, in vehicles, you see a spark plug is there, so that again creates a small energy, or the activation energy that is required, and the chemical starts reacting. So after that we will have a reaction, and finally you will have products of combustion, or products of POR, products of reaction. So this is the 4 steps that is follow. Okay, now to give energy, you can either give plugs or AC current also will create, right? Again, that is also a spark. Okay, so yeah, that is about combustion. Now moving on to, yeah, mixing also is very important, because if you do not mix, so for example, if you have a very drastic difference in densities of gases, you just uh, mix with 2 tubes, they will not get mixed, right? So that is again a problem. If it is not mixed, again the probability of finding, let's say you have CH4 and oxygen, let's say these two are not mixed very properly, then at one place you will find only oxygen rich, and at one place you will have methane rich. Now whatever the portion that is in contact between CH4 and O2, they will get combust, right? These guys will not participate. So okay, that's why the mixing is very important. Okay, if you have a poor combustion, whatever this guy is there, it will be wasted. Again, that will create a lot of things. You will have pollution, expensive to run, because every time you're wasting some of your reactants, right? Yeah, so that is about the combustion. Again, why do we do the combustion? Combustion is to get as much as heat energy from your reactants as possible. Okay, and also, see, whenever you heat something, let's say we will discuss in this in the next few slides. Okay, now that is all about combustion. And you can even you can characterize, there are different ways to characterize them. Okay, so you need to take different chemicals to absorb either, if you are talking about carbon dioxide, if you are talking about chlorine. So for chlorine you can use alkali to absorb, so that will tell you the amount of chlorine has been absorbed. So similarly you can use different moisture trappers. So there are different trapping materials which can trap different gases, and you can measure the amount that has been there. Okay, So now coming to, let's talk about the excess. Now we are talking about excess, right? So let's do the material balance for excess air. We didn't do the material balance for this exercise, right? Okay. Now let's say I have a coal. Coal is made up of 72% of carbon, 4% of hydrogen, 2.8% of nitrogen, 4.8% of oxygen, 3.2% of sulfur, 13.2% of ash. So this is a dried coal, right? It is heated above 120 degrees centigrade. So to remove moisture, right? Now we are using air to combust, right? To combustion. Now what is my air? So we are using 20% excess. Remember. So that means if I'm using X meter cube of air, then that means my total air will be 0.12, or I can call it as so my total air is 1.2. That means 100 plus 20, that is 120. So instead of writing divided by 100 will give me 1.2 meter cube. This is the amount of air we are using. Now I know what is my mass of carbon. Okay, again let's assume 1 ton of coal, okay, or you can take 100 kg also, that will not make a big dent. Okay, so let's take how much, 1000 kgs, or you can take 100 also. So let's take 100 for simplicity. Okay, so 72, right? Then 72 grams of carbon. So let's draw a table initially, and also let's take coal is 100 kilograms. Okay, so coal is 100 kilograms. Then carbon is 72%, right? So 72 grams, 72 kgs. Let's write mass. Okay, mass, and 72 . Okay, so again I have molecular weight, which is 12. So 12 672, right? So that means 6 moles of carbon is required to, again I know the carbon reaction, right? Let's write reactions here. This is my CO2 and H2, H2O, there is sulfur. Let's say my nitrogen is inert. Let's write it in red. My nitrogen is inert, my ash is inert. Okay, so what is again, we will remove the oxygen part. Okay, there is no need to worry about it. These two guys are inert, right? So apart from the oxygen present here, we are also supplying oxygen from air. Okay, that's why we remove this part whenever we are trying to calculate the net calorific value. Okay, so now 12 grams, right? 6 moles. So 6 moles is nothing but, you need 60, right? So 60 moles or 60 kilogram per mole of oxygen is required, right? So oxygen required is 6 or kg per mole. You can write it. Okay, now moving to hydrogen. Hydrogen is my 4%, that means 4 kilogram. So molecular weight will be divided by if I divide it by 2, that will be 2. So 2 moles will require half mole, right? So that means 1 mole. Oh, okay, just a second. So 2 moles, that means 4, right? If I'm saying 4%, that means 4 kilogram. 4 kilogram will, let's say 4, if I divide it by 2, the molecular weight is 2, right? So how many moles? I need 2 moles. Okay, so 4 is 2 times 2. Okay, so 2 moles of hydrogen is required, and that will react with how many? 2 moles means half, so that is 1 mole. 1 kg per mole required. Now sulfur is how much? 3.2, so that is 32 kgs. Oh, 3.2, right? So it is 3.2 kgs. Molecular weight is 32, then that should be 0.1 mole. So 0.1 mole will require 0.1 mole, and this is, and yeah, there is oxygen also, because oxygen is, even though not reacting, we have to remove that, right? Theoretical oxygen required to combust, because oxygen and oxygen will not react until unless you shove some UV rays, right? So we are not involving UV rays, so oxygen will, whatever the oxygen supplied from air will not react with oxygen present in your coal, right? So we need to write it in red because we need to remove it, right? We are only calculating the amount of oxygen required from these guys. Okay, so that will be 6 plus 1 plus 1. So this will be equals to 1 oxygen. How much oxygen is there? It is 4.8, right? 4.8 means oxygen weight is 32, so it will be 1.5, right? So it will be 0.15. So it will be 0.15 kg per mole, or moles or kg per mole. It is kg per mole. Okay. Now theoretical oxygen that is required. So we have 6 plus 1 plus 0.1, and that will give me 6, 7. Okay. So 7 plus 1, 7.1 minus our 0.15. This will give me 6.95 kg per mole of oxygen that is required to burn, right? Now if I do it, so then what is my nitrogen in air? So nitrogen in air will be 6.95 times 3.76, right? So that will be equals to 2.6132 kg per mole. So this is the nitrogen that is present, right? Now what is the oxygen? Oxygen is stoichiometric plus excess, right? So that's why 69 or 6.95 times 1.2, and this will give me 8.34 kg per mole. This amount of moles is required. So for example, everything get combust. Okay, combustion is done. So then oxygen that is remained in my product will be, so oxygen remained in products of combustion. See, excess is only supplying to increase the surface. The interaction between the fuel and air. It's not so that to giving excess air to burn. No, just like whatever the oxygen is required, that is only getting converted and reacted. Whatever the excess is there, it will still remain. It will not react. So it's like this. So for example, if I have M that is reacting, if oxygen is surrounding from everywhere, okay, but M only requires 3 moles, so it will only take 3 moles. The other 3 moles are left behind. Okay, so it is just so that to increase the reaction area between the M and the oxygen. Okay, our excess will be 0.2 times 8.34. Okay, so or you can take into 69.5, and that will give me 1.39 kg per mole. Okay, so that is about that. Now, so why I am writing theoretical air? See, this is theoretical air. There is not the amount of oxygen required. It is the theoretical air that is required. Okay, there is an oxygen that is required to combust. Because if I add again 0.15, there will be excess of 0.15 coming from coal. So that's why we removed it. Because whatever the oxygen that is supplied from air will not react with this oxygen in coal, right? So that's why we removed this 0.15, and this is the amount of air present in, see, amount of oxygen, right? It's the amount of oxygen should be present in air. This is 6.95 kilograms per mole. Now again, the next one is the actual air required, right? So again, that is same, 83.4. Which one is, 8.34, right? So theoretical air, we know, right, how much the theoretical air is required. Okay, so from this you can find the other things, right? Total amount of, if I remove the moisture, then it will be products of combustion of dry one, and whatever, if I want to calculate the total amount of products that has been formed, again that is easy, right? So I know amount of carbon dioxide that will be produced. If I know the amount of carbon that has been used, same process. Okay, so there is no much difference. Okay, now moving on to, so what are these things? So this is the oxygen, excess oxygen is there, so oxygen present in the products of combustion. Okay, now let's do a different problem. Okay, or we can even calculate, gross calorific value or net calorific value. Oh, we need to find net calorific value also, right? So what is my net calorific value? NCV, again I will write that formula. So 81 times C, what is the amount of carbon that is been present? That is 72 plus 34, 341, again 4 minus 4.8 divided by 8, that is right, 4.8 divided by 8, plus 22 times 3.2 amount of sulfur. Because it is on dry basis, right, there is no moisture, it is 5.84 into 9 times 4, 9 3 times 4, 36, right, 36. So this value will be 6851.56 kilocalorie per kg. So I already did this, so I'm just pasting that value. Now if you want to joules, you can just multiply with 4.184186. Okay. Now if I want to total CV, that calorific value that has been produced, you just multiply it with 100 because we used 100 kilograms, right? Now if you use the enthalpy of formation, right? So whenever if I talk about there is an enthalpy of formation, see, because every reaction has some delta H formation, right? So again, if you use that, again there will be some difference coming. Okay, so calorific value, let's say if I want to calculate it, so amount of carbon is 6, right? If I turn everything into volume fraction, right? If I turn everything into volume fraction, and then if I want to find out the percentage of composition of gases, you can do Orsat analysis. So Orsat analysis, again different adsorbing chemicals will be there which adsorb each type of chemical. Okay, so that will give you flue gas composition, or flue gas is nothing but your products of combustion gas. Okay, now if I choose the enthalpy values, and the standard enthalpy of formation of carbon dioxide is minus 393.509 times 6 moles, right, plus 241.818 into 2, which is the amount of hydrogen, and 296.84 plus 296.84, right, into 100, right, you will get 2874374. Okay, this is your kilojoules. Once I convert it into calories to kilojoules, so you will have some differences, but the differences will not be very large. Okay, it might be less than 1%. Okay. So either you can use this or you can use the formula above. So either you can use standard enthalpy of formation, or you can just combustion, find out what is the amount of energy that is being produced. Okay, so let's see what about the incomplete combustion. Okay. Now if I want to know the incomplete combustion, then you need to know what is the percentage of CO to CO2 ratio. Okay. This ratio is very important because what it says is some amount of carbon is being completely oxidized, some amount of carbon did not oxidized. Okay, so once you know what is the ratio, then you can get x and y part. Okay, so if I know the x and y part, I can back calculate what is the amount of carbon that has gone into this reaction, and from there we can calculate what is the percentage of oxygen that is required. Okay, the theoretical oxygen that is required. Okay, let's say our ratios are 1:1. Okay, let's not complicate. So for incomplete combustion, you have C plus O2 CO2, and C plus CO2 gives us to 2CO. So you can either take this reaction CO2, again it reacting with carbon to form CO. Okay, to avoid oxygen, right, to avoid oxygen writing many times, you can just take this reaction. Okay, what you do is you just reverse this reaction and then you add it. So carbon will go away, you will be remained with oxygen. Okay, so yeah, this is one reaction. And then now if I try to write, or let's say write for this, let's write it in terms of enthalpy ratio. Okay, So then amount of carbon that is been reacted here, okay, so that will be 1 the enthalpy of formation of CO2 will be, or CO2 will be 1525 times 6, because we are only considering 100 kgs, okay, plus the standard enthalpy of formation of, okay, so this is for CO2, CO, okay, standard formation of CO, right? So the amount of carbon will give you the amount of CO, okay, so 110.525 into 6 plus into 60 plus, what about this one, is that 241.818 into 20 plus 296.84 into, okay, let's say we have only carbon monoxide, there is no complete combustion, only total carbon monoxide, okay, so everywhere you will find carbon monoxide, there will be no carbon dioxide, okay, so then if I remove this guy, then 110.525 into 6, right, so whatever the carbon is there, that are totally getting used to get CO. Now finally you will get the value, so that is how we do it. Now that is about mass balance, okay. Now let's move to this heat balance, okay, let's do it fast. Heat balance is again same, all you need to do is CP values, the CP values will come. Let's do it in 5 minutes, okay, we have already gone past our time. So from where the heat is getting, how to do the heat balance, so heat is coming from the sensible heat, I mean the heat that is being carried by the reactants. Sensible heat from reactants, what are the reactants? Air plus fuel, plus whenever this air and fuel will react, it will give heat, and that heat is coming from combustion. So heat coming from combustion, okay, and once if something happens, so let's say two gases are fuel, let's say fuel and air are being first, and then we lighted it, so some amount of is going in terms of light and heat energy, so that is heat loss to surroundings, plus if heat carried away by POC, heat carried, or sensible heat, you can write as sensible heat, sensible heat of POC, products of combustion, plus if some POCs get dissociated, right, dissociation, that again requires heat, so dissociation of POC, yeah, so these three will go, and these two will go, and these three will come up, right? Now there are some, these like exact, this is the exact rule that we should follow, but for assumptions we remove this part, okay, so this part is removed, this is assumption, again this is also removed, so assumption 1, assumption 2, so our first assumption will be for theoretical, I mean to get theoretical max flame adiabatic flame temperature. Adiabatic flame temperature is nothing but this whole thing is surrounded, there is no heat loss, actually it is not possible, it is some amount of will be lost, so that means the adiabatic flame temperature is nothing but this flame temperature in adiabatic conditions, so there is no heat going outward, everything is covered by adiabatic walls, okay, so again there is no dissociation of products, whatever the combustion products you got, there is no dissociation, So that is assumption 1 versus assumption 2. So whatever the sensible heat that you are giving, and the heat of combustion is directly going into sensible heat of products. So if I know the sensible heat of products, then I can backtrack this, right? I can back calculate the heat of combustion and sensible heat. Okay? So but it is not possible. I mean, not possible, but that case is not possible, right? You cannot contain heat, right? So that's why you have theoretical max adiabatic flame temperature, which is less than adiabatic flame temperature, which is it is greater than, right? It is greater than adiabatic flame temperature, right? Which is again greater than actual flame temperature. That's what we see, right? And again the next assumption we can take is Cp values. See, Cp is a function of strong dependent of function of temperature. So that is A plus Bt plus Ct square plus D divided by T square plus E ln T. So there are terms that will appear more and more. So for now we can assume that at certain temperatures, certain Cp values of certain compounds will not change with temperature. Let's assume they are not changing drastically with a temperature. Okay, so then you can avoid all these terms again, which will not give a good value. But for assumption basis, we can just assume A. Then we know del H. If I want to know dH, is NCP dt. If Cp is only a function of it doesn't depend on temperature for now, for assumption wise, then you can just del H, it will become del H, okay, from 298 to at a certain temperature, and will come out, Cp will come out because it is not a function of temperature, right? Then you will only have delta T, and this delta T is T minus 298 Kelvin, the temperature at which adiabatic flame temperature at which it is happening, minus 298. If these terms are included, then you cannot avoid, then you painfully have to do the integration. Okay, so let's do for one thing. Okay, now let's do for the first problem, okay, that we have did, right? So we know let's calculate the amount of values. You can get the Cp values from net itself. You can follow the standard values from Gaskell also, which is from thermodynamics of metallurgical thermodynamics book. Okay, so the amount of Cv that we have got there was 2874,374. This is the amount of that we have generated, right? And that will be equals to into 100, because we are talking about 100 kilograms of coal, right? So that will be equals to how much? 100 into, so 262.32 will be our what, nitrogen, right? 262.32 into 7.12, which is the enthalpy value, times 60, not 60, 262, it is 26, right? 26.232 into 6 into 12.5 plus 2 into 7.73 is for hydrogen, is for oxygen, is for hydrogen, plus 1 into 13.0.1, okay, 13.5, and 13.5 is for S4 2, sulfuric acid, sulfur oxide, right? Sulfur dioxide, not sulfur oxide. Okay, 0.1, and 6 is coming from your carbon. 6 kgs are coming from carbon. Sorry, 6 moles are coming from carbon. 2 moles coming from your H2 hydrogen, right? So 0.1 from 13.5 of sulfur dioxide. This is for nitrogen. This is for carbon dioxide, because carbon is 6 moles of carbon will react with 6 moles of oxygen to give 6 moles of carbon dioxide, and 2 moles of 1 mole of hydrogen, 2 moles of hydrogen will again react with 1 mole of oxygen to give 2 moles of water. So that is here. Now all I have to do is just calculate. Now there is the next term, and here you will have 4.184. Why? Because we calculated in calories. Now we have to convert into joules, right? Because this is in joules, so we need to convert this calories into joules. Okay. So this, and the temperature, the final will be T minus 25. Okay. Or if I am talking about in degree centigrade, we can write 298. Okay. And the final will be 2491 degrees centigrade. So that's it. You just add Ni, Ci, or CVI. CV is, or CPI. CP is specific heat capacity at constant pressure. So you just add number of moles of nitrogen if this Cp is not a function of temperature. If it is a function of temperature, you cannot directly add this. Okay, you just take number of moles of nitrogen times Cp of nitrogen plus number of moles of carbon dioxide times Cp of carbon dioxide, number of moles of H2O times Cp of H2O, number of moles of sulfur dioxide times Cp of sulfur dioxide. Then you multiply it with 100 because it is 100 kgs, and times 4.184, which is for joules to calories conversion ratio. So this will give you final into T minus Tf, or Tf minus T, or T initial. That's what we did. So finally you will have 2491 degrees centigrade. If I am talking about with excess amount of oxygen, then what you need to do is you need to add oxygen also, right? Because oxygen is also getting heated up, right? So for that, here you just need to add what is the Cp of oxygen, right? We need to know 7 point, so excess will be 13.1.39, right? It is 1.39 moles of oxygen. In previous problem we derived, right? Excess oxygen product gas that has been left. Okay, so that is 1.39 times Cp of oxygen is 7.61. That's it. We just add this guy here if excess is purged. This is according to question 1. Okay, if excess oxygen is purged, that's it. Then your temperature will slightly change. Why? Because some amount of energy is eaten away by oxygen, right? Oxygen will also heat up, right? So that's why the temperature drop will be 2139 degrees centigrade. Okay. That's it. That's all. Okay. See, why the value was same? Because even though I removed 10 from here, again I am using 10 from here. So that's why the slide whatever the value you got in slides, and here the number is same, because it's just the proportion has changed, right? Okay. So that's all. Okay. So that's all for today's session. If you have any doubts, you can stay, or if you do not have any doubts, you can leave. Let me stop the recording.